Happy to welcome you all, my dear students. In today's video, let's learn about electrochemistry and the basic terms involved. Electrochemistry is the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical transformations. The subject is of importance both for theoretical and practical considerations. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals are produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on a large scale in various instruments and devices. The reactions carried out electrochemically can be energy efficient and less polluting. Therefore, study of electrochemistry is important for creating new technologies that are eco-friendly. Even in our own body, the transmission of sensory signals through cells to brain and vice versa and communication between cells are known to have electrochemical origin. What is electrochemistry? Electrochemistry is the study of chemical reactions which take place at the interface of an electrode, usually a solid, metal or semiconductor, and an ionic conductor, which is the electrolyte. Electrochemistry deals with the interaction between electrical energy and chemical change. Now, what is an electrochemical reaction? If a chemical reaction is driven by an external applied voltage, as in electrolysis, or if a voltage is created by a chemical reaction, as in a battery, it is an electrochemical reaction. A galvanic cell is an important electrochemical cell. It is named after Luigi Galvani, an Italian physicist. It's also called the voltaic cell, which is named after the Italian physicist Alessandro Volta. A galvanic cell generally consists of two different metal rods which are called electrodes. Each electrode is immersed in a solution containing its own ions, and these form a half cell. Each half cell is connected by a salt bridge or separated by a porous membrane. The solutions in which the electrodes are immersed are called electrolytes. The chemical reaction that takes place in a galvanic cell is a redox reaction. One electrode acts as the anode, in which oxidation takes place, and the other acts as a cathode, in which reduction takes place. The best example of a galvanic cell is the Daniell cell. One electrode, there is oxidation taking place, which means it loses electrons. The other electrode gains electrons. So if it is gaining electron, that process is called reduction. Loss of electron, LOE, is oxidation. So this is the pictorial representation of a Daniell cell where the copper electrode is immersed in a solution of copper sulfate, and zinc electrode is immersed in a solution of zinc sulfate. At the anode, zinc undergoes oxidation. So at the anode, zinc is undergoing oxidation to form zinc ions along with electrons, electron liberation. So the zinc ions pass into the solution. If the two electrodes are connected using an external wire, the electrons produced by the oxidation of the zinc will travel through the wire and enter into the copper electrode, where they reduce the copper ions present in the solution and form copper atoms that are deposited on the cathode. At the anode, the reaction that is taking place is represented like this. Zinc is the anode, it is losing electrons and forming zinc ions. At the cathode, the reaction that is taking place is the copper ions are accepting the electrons and it is forming copper. The movement of electrons from zinc to copper produces a current in the circuit, and the net chemical change described as the cell reaction is the sum total of the two reactions at the cathode and the anode. So the sum total of these two is written as Zn plus Cu2 plus gives Zn2 plus Cu. Now, what is a salt bridge? The salt bridge is usually an inverted U-tube filled with a concentrated solution of salts like KCl, KNO3 or ammonium nitrate, which can be used as the electrolyte here. A tube or membrane packed with a solution of the salt composed of the ions which are not involved in the reaction. These ions just permit the exchange of charge in order to balance the charge. Now, how is this salt bridge made? To prepare the salt bridge, agar-agar or gelatin is mixed with a hot concentrated solution of the electrolytes like KCl, KNO3 or NH4NO3 and is filled in the U-tube. On cooling, the solution sets in the form of a gel inside the U-tube, which prevents the intermixing of the fluids. The two ends of the U-tube are then plugged using a wool to minimize the diffusion. Now let us learn the significance of the salt bridge, or what is the use of this salt bridge. The salt bridge, its main function is to prevent the potential difference that arises between the two solutions when they are in contact with each other. This potential difference is called the liquid junction potential. It completes the electrical circuit by connecting the electrolytes in the two half cells. It prevents the diffusion of solutions from one half cell to the other. It also maintains the electrical neutrality of the solutions in the two cells. Now, there is another question which is arising always, asking why the solutions like KCl or KNO3 or ammonium nitrate is selected in the salt bridge. The salt bridge, already we learned the function that it helps in the migration of ions from one side to another. As the transference number of cation and anion in KCl as well as KNO3 or ammonium nitrate are approximately equal, we are choosing these solutions. And as these ions carry the current in a salt bridge between the two half cells, the rate of the movement of the charge in the opposite direction will be approximately same. Secondly, there will be no charge separation across the solution interface. In this way, no formation of charge layers and thus liquid potential can be eliminated. Any electrolyte in which the transport number of cations and anions is same is successfully used as a salt bridge. That is why KCl solution is commonly used as a salt bridge. Now, let us learn how to represent an electrochemical cell. In an electrochemical cell, the anode is written on the left hand side and the cathode is written on the right hand side. The anodic cell is written by writing the metal first and the metal ions present in the electrolyte. These two are separated by a vertical line or a semicolon. So these are the two forms in which you can represent an anode. The molar concentration or the activity of the solution is written in brackets after the formula of the ion. So here we have written the molar concentration within brackets as 1m. The cathodic cell is represented by writing the metal ion first and then the metal. Both are separated by a vertical line or they can be separated by a semicolon. So these are the two different forms in which you can represent the cathode. The molar concentration or the activity of the solution is written in brackets after the formula of the ion. For example, a copper cell is represented as Cu2 plus, whose concentration is 1 molar, then a vertical line, then Cu or slash Cu. Instead of the slash, you can also use semicolon Cu. A salt bridge is represented by two vertical lines. So a Daniell cell can be written like this. This is the anodic half cell, zinc slash Zn2 plus, or Zn slash Zn2 plus is the anodic half cell, and Cu2 plus slash Cu is the cathodic half cell. Both are written like this, anode on the left hand side, cathode on the right hand side, separated by a double line which is indicating the salt bridge. If the concentration of both the electrolytes is 1 molar, then the cell notation is written like this. You write the cell, half cell, Zn slash Zn2 plus, and near the ion we have to write the concentration of the ion as 1 molar. This is a salt bridge. Then Cu2 plus 1 molar slash Cu. So this is how the cell notation is represented. Next we learn about reversible and irreversible cells. Daniell cell and secondary batteries are all rechargeable batteries, and a very good example for reversible cell is a Daniell cell whose EMF is 1.1 volt. A Daniell cell can be represented like this: Zn slash ZnSO4, concentration 1 molar, salt bridge, CuSO4 1 molar slash Cu. This cell obeys the following three conditions of thermodynamic reversibility. That is why a Daniell cell is called a reversible cell. If the Daniell cell is connected to an external source of EMF equal to 1.1 volt, no current flows and also no chemical reaction takes place in the cell. If the external EMF is made slightly less than 1.1 volt, a small amount of current flows from the cell and a small chemical reaction occurs. If the external EMF is made slightly greater than 1.1 volt, the current will flow in the opposite direction. Copper will pass into the solution as copper ions and zinc will get deposited on the zinc electrode. Since the Daniell cell obeys all these principles, it can be considered as a reversible cell. Next one is a irreversible cell. Zinc silver cell is a irreversible cell, or a dry cell is also a irreversible cell. Any cell which do not obey the conditions of thermodynamic reversibility are called irreversible cells. Zinc silver cell is an example for irreversible cell. Zinc silver cell can be represented as zinc Zn/H2SO4/Ag. The cell reaction that is taking place at anode is zinc reacts with sulfuric acid forming zinc sulfate and hydrogen. At cathode, the silver ions accept the 2 electrons and form silver and are deposited as silver. Since at the anode itself, one of the product formed is hydrogen and it is escaping away as gas, the reversible reaction cannot happen. That is why these cells come under the classification or classified under irreversible cells. Thank you for watching. Stay tuned to watch our next video on electrode potentials.